Hello, my friend. You found your way to a quiet corner of the universe, just in time to rest your thoughts. Tonight, we'll drift gently through the mysteries of the quantum vacuum, the so-called nothing that might be everything. You don't need to focus or stay awake. Just let your mind wander, and I'll take care of the rest. Chapter 1. What is a vacuum, really? In everyday language, a vacuum is thought of as empty space, something devoid of matter, of sound, of substance. We think of it as a void, a region where nothing exists and nothing happens. In classical physics, this idea was formalized as a perfect vacuum, a space entirely free from particles, air, or energy. The kind of nothing you might imagine between stars or in a laboratory chamber evacuated of every gas molecule. But in quantum physics, this idea collapses. The vacuum, as understood by modern physics, is not a barren void. It is a dynamic, restless field of invisible activity where the absence of matter is not the absence of existence. It is, paradoxically, the most active state of all. To understand this transformation from classical emptiness to quantum fullness, one must first let go of the notion that space is simply a backdrop for events. In Newtonian physics, space and time were the absolute stage on which particles danced, unchanging, passive, and eternal. Remove all particles and the stage remained, flat, mute, and empty. This concept reigned for centuries until it was upended first by relativity and later by quantum field theory. Albert Einstein's theory of general relativity shifted the paradigm by showing that space is not an inert arena. It bends and curves in the presence of mass and energy. Gravity, in this framework, is the geometry of space itself. So even in the absence of matter, the stage could flex and warp, given the right conditions. But it was the quantum revolution that shattered the idea of a tranquil vacuum entirely. In quantum mechanics, particles are not tiny solid spheres, but excitations of fields that permeate all of space. There is an electron field, a photon field, a quark field, all invisible yet everywhere. A particle is simply a local disturbance in one of these fields. You might picture the vacuum as a completely still pond. But in quantum mechanics, this pond is never still. Even in its lowest possible energy state, its so-called vacuum state, it seethes with fluctuations. These quantum fluctuations are not an artifact of poor measurement or hidden variables. They are a fundamental feature of nature. Due to the Heisenberg uncertainty principle, energy and time are entangled in such a way that it is impossible for any region of space to have exactly zero energy over any finite duration. What this means is that, for very short intervals of time, the energy of a region can deviate from zero in ways that permit fleeting, virtual particles to emerge and vanish. These particles are not directly observable in the traditional sense, but their effects are real. They influence forces, shift energy levels, and in some cases, push physical objects. One of the earliest signs that the vacuum was not truly empty came from the study of atomic spectra. Physicists noticed tiny shifts in the energy levels of electrons orbiting hydrogen atoms that could not be explained by classical or even basic quantum models. The solution came when quantum electrodynamics, or QED, was applied. In this framework, the electron interacts not just with the nucleus, but also with the frothing quantum vacuum around it. This vacuum briefly spawns virtual photons and electron-positron pairs that slightly alter the electron's behavior. The result is the Lamb shift, an experimental confirmation that even in deep emptiness, something remains. The quantum vacuum also plays a role in force mediation. The electromagnetic force, for instance, is carried by photons. In quantum field theory, even the so-called force between two charged particles can be interpreted as the exchange of virtual photons arising from vacuum fluctuations. These exchanges do not require the presence of real photons. They are consequences of the uncertainty and richness of the vacuum itself. Another striking demonstration of the vacuum's reality is the Casimir effect, in which two uncharged metallic plates placed very close together in a vacuum experience an attractive force. This occurs not because of any direct interaction between the plates, but because the vacuum fluctuations between them are restricted compared to the fluctuations outside. The plates feel a push, not from a wind or a field, but from the vacuum itself. This invites a deep realization: the vacuum is not nothing. It is a physical state with measurable properties. It has energy, it exerts pressure, and it can influence matter. In fact, when quantum field theory is used to calculate the energy density of the vacuum, the result is not zero, but a staggeringly large number. So large that if it were accurate, the universe would have torn itself apart long ago. This discrepancy between theory and observation is one of the greatest unsolved problems in modern physics, and is sometimes called the cosmological constant problem. Physicists suspect that some mechanism, perhaps involving cancellations or symmetries, reduces the effective vacuum energy to an incredibly tiny value. Still, it's not zero. The expansion of the universe is accelerating, and one explanation is that vacuum energy, also called dark energy in this context, is driving this acceleration. If this is true, then more than 2/3 of the energy content of the cosmos may be stored in empty space itself. On a smaller scale, the quantum vacuum is essential to modern physics. Particle accelerators probe the vacuum not by entering it, but by smashing particles to disturb it, to stir it up until excitations, new particles, emerge from it. Every particle we observe may be viewed as a localized ripple in an omnipresent field, and these fields are never fully dormant. Even in the deepest interstellar void, far from any star or galaxy, these quantum fields remain, fluctuating with undetectable energy until they are stirred into observability. What makes the quantum vacuum even more remarkable is that it seems to define what can be, not just what is. The structure of the vacuum determines which particles are possible, how they interact, and what forces govern them. It's not simply a background, it is the foundation. Just as the structure of a crystal determines how light travels through it, the structure of the vacuum defines the rules of the universe. And yet, for all this richness, it is still, in some ways, nothing. It cannot be touched or seen directly. It is elusive and silent. It resists our classical intuition. When we imagine emptiness, we picture stillness. But in quantum physics, stillness is impossible. Every point in space is a sea of possibility. And in that sea, the notion of nothing dissolves. The quantum vacuum also plays a pivotal role in more speculative branches of physics, particularly those that attempt to unify quantum mechanics with gravity. In attempts to construct a theory of quantum gravity, a consistent framework where both quantum principles and general relativity coexist, the vacuum becomes not just a passive stage, but a dynamic player. In loop quantum gravity, for example, the fabric of spacetime itself is thought to be quantized. This would imply that even the vacuum state of spacetime might be granular at incredibly small scales, composed of loops or networks. In string theory, another contender for a theory of everything, the vacuum is even more elaborate. The number of ways that extra dimensions can be curled up, compactified, defines a vast landscape of possible vacuum states, each corresponding to a different set of physical laws. This landscape of vacua suggests that our universe's version of the vacuum is just one of many possible configurations, perhaps selected randomly or anthropically from a multiverse of options. This idea remains highly theoretical, but it underscores how central the vacuum is to any vision of fundamental reality. It is not a byproduct or a detail. It is the stage, the script, and in some interpretations, the director. The idea that there could be multiple vacua is not limited to string theory. In quantum field theory, the concept of vacuum degeneracy allows for different ground states, each associated with different symmetries and particle content. In the early universe, it is thought that a process known as spontaneous symmetry breaking led to a transition from a more symmetric vacuum to the one we observe today. This transition may have released vast amounts of energy, fueling cosmic inflation, a brief but explosive expansion that shaped the observable universe. In essence, the vacuum is not just foundational, it is historical. The vacuum we inhabit is not the only one that could exist, nor is it necessarily eternal. It may have emerged from a different state, and it may one day transition again. Such a shift would be cataclysmic, altering the laws of physics in a flash. This terrifying idea, called vacuum decay, is a legitimate prediction of some quantum field theories, although there's no evidence it's imminent. Even at the edges of what is scientifically accepted, the vacuum's importance holds. Whether it's the speculative creation of the universe from a quantum fluctuation, or the possibility that consciousness itself may emerge from a fundamental interaction with quantum fields, the vacuum provides fertile ground for exploration. It is the closest physics comes to addressing the mystery of how something comes from nothing. And yet, it's not really nothing at all. The vacuum reminds us that our most intuitive concepts of space, of time, of absence are not fixed. They are subject to revision, to deepening as our understanding grows. There is no stillness beneath the surface, only motion too subtle to see. No silence, only frequencies beyond our hearing. No emptiness, only forms of presence waiting to be perceived. We often fear the void, imagine it as the absence of meaning or being. But perhaps the void is not what lies beyond the world. Perhaps it is the world itself, unshaped but full of shape, unseen but full of vision. Chapter 2. Virtual Particles, Borrowing Existence from Time. To understand virtual particles is to step further into the strange fabric of the quantum vacuum. These are not particles in the way we normally imagine them. They are not little solid objects flying around, bumping into things, or being captured by detectors. Virtual particles exist on the edge of what can be called real. They do not persist long enough to be observed directly, yet they exert influence. They shape the very forces of nature and govern interactions between what we can see. They emerge from the vacuum for the briefest flashes of time, then vanish without a trace. Ghosts that leave behind measurable consequences. In classical physics, there is no room for this kind of ephemeral existence. A particle is either there or it isn't. But quantum mechanics, and especially quantum field theory, rewrites that logic. In these frameworks, every fundamental force and every particle arises from an underlying quantum field that spans all of space. What we call a particle is just a localized excitation of that field, a ripple that can move, interact, and sometimes be detected. But the field doesn't sit idle between those excitations. Even in its lowest energy state, the so-called vacuum state, the field is still alive with activity. The energy of the vacuum never truly drops to zero. According to quantum principles, particularly the uncertainty relation between energy and time, the vacuum can briefly borrow energy so long as it returns it quickly enough. This temporary energy can give rise to what we call virtual particles, entities that exist only for such short durations that they cannot be directly detected, but long enough to play a role in quantum processes. These particles are called virtual, not because they are imaginary, but because they do not fulfill the same criteria as real particles. A real particle can be observed, measured, and assigned a well-defined energy and momentum that satisfies Einstein's famous relation for mass and energy. A virtual particle, by contrast, is an internal component of an interaction, something that appears in the mathematical description of a process, but cannot exist independently in the universe for more than a fleeting moment. It exists within the calculations, within the logic of the quantum world, and yet its effects are real. Consider the electromagnetic force. When two electrons repel each other, quantum field theory describes this interaction not as a smooth force field pushing them apart, but as an exchange of virtual photons. These photons are not real particles that can be captured in a detector. They are never directly seen, but their role in mediating the repulsion is well understood and mathematically necessary. They are the carriers of the force, not as solid messengers, but as probabilistic intermediaries that arise out of the vacuum and vanish back into it, obeying the uncertain rules of quantum energy. Virtual particles also emerge in loop corrections in particle physics, where they temporarily alter the behavior of real particles. For instance, when an electron propagates through space, it is not merely drifting alone. The quantum vacuum surrounding it teems with activity. Virtual electron-positron pairs may briefly emerge and recombine, altering the electromagnetic field in the process. The electron, passing through this sea of fluctuations, effectively acquires different properties than it would have in a classical empty space. Its mass and charge are subtly shifted, a process known as renormalization. Without virtual particles, the theoretical predictions of particle physics would not match experimental observations. This interplay between vacuum fluctuations and observable behavior is not just theoretical. There are real-world measurements that confirm the presence and influence of virtual particles. One of the most famous examples is the Lamb shift, a tiny shift in the energy levels of hydrogen atoms that cannot be explained without accounting for the interactions between electrons and the fluctuating vacuum. The vacuum is not silent, and virtual particles are not a curiosity. They are required to explain the precision of atomic spectra. Another example is the anomalous magnetic moment of the electron, one of the most precisely measured quantities in all of physics. The observed value deviates slightly from the prediction made by simple quantum mechanics. But when quantum electrodynamics includes the effects of virtual particles, specifically, the continuous creation and annihilation of virtual pairs and photons, the prediction aligns with observation to many decimal places. The virtual is not speculative, it is necessary. Yet it's important to note that the language of virtual particles, while useful and evocative, is still a product of the methods we use to compute physical processes. In the formalism of quantum field theory, interactions are often calculated using perturbation theory, a method that breaks down complex phenomena into manageable pieces. These pieces are visualized using Feynman diagrams, where real particles travel in and out of interactions, and virtual particles appear as internal lines, participants in the process, but never visible to the outside world. These diagrams are not pictures of what's actually happening in space and time. They are representations of mathematical terms in a complex expansion. The virtual particles we draw and talk about are convenient tools to keep track of what is happening inside a quantum process. Some physicists argue that taking them too literally can be misleading. Others argue that even if they are not real in the traditional sense, they are indispensable to understanding the mechanics of the universe. Still, their effects remain. In addition to shifting energy levels and mediating forces, virtual particles are involved in phenomena like vacuum polarization, where the vacuum behaves like a dielectric medium that changes the apparent behavior of electric charges. This can be viewed as virtual pairs in the vacuum, aligning themselves in response to an external field, just as molecules in a dielectric align in classical physics. The result is a shielding effect, subtly altering the effective charge of particles like the electron. Again, these effects are not hypothetical. They have been measured and accounted for in highly accurate experimental data. Virtual particles also appear in more exotic contexts, especially when gravity enters the picture. In curved spacetime or accelerated frames of reference, the definition of what counts as a particle becomes ambiguous. According to the Unruh effect, an accelerating observer can detect particles in a vacuum that an inertial observer would consider empty. From this point of view, the vacuum is not an absolute concept. It depends on who is observing it. Virtual particles, once again, play a role in defining what is real and what is not. This observer dependence becomes even more dramatic in the context of black holes. According to Stephen Hawking's prediction, black holes are not entirely black. They emit radiation due to quantum effects near the event horizon. This so-called Hawking radiation can be understood loosely as arising from virtual particle pairs that are separated by the black hole's gravity. One falls in, the other escapes. Though this picture is simplified, it captures the essence of how virtual particles influence the most extreme environments in the universe. Yet even here, the terminology can lead to misunderstandings. The virtual particles in this scenario are not literal particles popping in and out of space like bubbles in boiling water. Rather, they reflect a change in the vacuum structure caused by gravity. The field itself, when analyzed near the event horizon, supports modes of energy that look like radiation to a distant observer. The mathematical machinery used to describe this radiation involves the same tools that introduce virtual particles elsewhere. They may be constructs, but they are powerful ones. Despite their elusive nature, virtual particles have become a fixture in the way physicists think about the quantum world. They help bridge the gap between mathematics and intuition. They give language to the invisible and offer a way to imagine what cannot be directly seen. But they also remind us that our understanding of nature is layered and that not everything useful must be strictly real. At their heart, virtual particles are an embodiment of quantum indeterminacy. They challenge the notion that energy and matter are fixed, concrete, and always subject to strict conservation laws at every moment. They show us that nature allows for ambiguity, for temporary bending of rules, so long as the accounting is settled in the end. And yet, these temporary fluctuations may underpin much of what we take for granted as stable reality. The constants of nature, the structure of atoms, even the strength of the forces that hold matter together, all are influenced by these fleeting, hidden participants. We live in a universe where the vacuum itself is not a passive absence, but a restless participant. Virtual particles animate that vacuum, whispering interactions into being, nudging particles along paths they wouldn't otherwise take, and leaving fingerprints on every level of the cosmos. Perhaps, in some abstract way, virtual particles represent the permission nature gives itself to explore possibility. They are expressions of the universe's willingness to experiment with what might be, even if only for a moment. They do not linger, but they matter. Their presence is felt, not seen. And maybe, just maybe, they remind us that even the briefest appearance can have lasting consequences. What we call nothing is far from empty. It is an ocean of transient sparks flickering in and out of existence, never staying, never resting. In that froth of potential, reality is not a fixed thing, but a constant negotiation. And we, too, are part of that dance, appearing, interacting, and vanishing, like a story told briefly across the fabric of time. Chapter 3. The Casimir Effect. Proof that nothing has pressure. There are few concepts in physics more counterintuitive than the idea that empty space can exert a physical force. Yet this is precisely what the Casimir effect demonstrates. In the stark silence of a vacuum where there are no particles, no gas, and no thermal radiation, a measurable force can arise, not from matter but from the structure of space itself. This phenomenon is one of the clearest and most elegant confirmations that the quantum vacuum is not empty, and it offers a rare glimpse into how quantum fluctuations, normally imperceptible, can produce tangible, macroscopic consequences. The Casimir effect was first predicted in 1948 by Dutch physicist Hendrik Casimir while he was working on theoretical models for van der Waals forces between neutral molecules. At the time, quantum electrodynamics was still being developed, and many of its predictions were untested. Casimir's insight was to consider how the quantum vacuum might behave when constrained between two conducting plates placed extremely close together, on the order of micrometers or less. What he found was astonishing. Even in the absence of any particles, the plates would experience an attractive force, as though being pulled together by invisible hands. The explanation lies in how boundary conditions affect the quantum fields that permeate space. In an unrestricted vacuum, all possible modes of electromagnetic radiation can exist, each with different wavelengths and energies. These modes are the vacuum fluctuations, the ever-present ripples in the quantum field, each contributing a tiny bit of energy to the overall vacuum. When two conducting plates are placed in close proximity, however, not all modes can exist between them. The plates enforce a condition that the electromagnetic field must vanish at their surfaces. This requirement restricts the allowed wavelengths between the plates to those that fit neatly in the confined space. Outside the plates, there are no such restrictions. All wavelengths are still allowed, resulting in a higher density of modes, and therefore a higher vacuum energy outside the plates than between them. The result is a net pressure pushing the plates toward each other. This is not a force caused by particles or thermal radiation, but by the suppression of vacuum modes within the constrained region. The plates are effectively being pushed together by the vacuum fluctuations of the quantum field that exist outside more robustly than inside. What makes the Casimir effect particularly fascinating is that it reveals a direct, measurable consequence of something previously thought to be purely theoretical. Quantum fluctuations, virtual photons, and the zero-point energy of the vacuum might seem like abstract ideas confined to the realm of blackboard equations and high-level mathematics. But in this case, they exert a real force that can be measured in the lab with extremely sensitive instruments. Over the decades, numerous experiments have confirmed the existence of the Casimir effect with increasing precision, using various materials, geometries, and environmental conditions. One of the most commonly used setups in experiments involves a metallic sphere and a flat metallic plate, which are brought close together in a vacuum chamber. This configuration avoids the alignment difficulties that arise with parallel plates. As the separation between the objects decreases, the Casimir force becomes stronger, following a specific distance-dependent relationship. The strength of the force is incredibly small, measurable only at distances less than a micrometer, but it is unmistakable. As measurement techniques have improved, physicists have confirmed the predictions of quantum field theory to within a few percent, reinforcing our understanding of the vacuum as a physical entity. In some cases, the Casimir effect has even been repurposed as a tool to explore modifications to quantum field theory. By studying how the force behaves under different materials, geometries, or temperature conditions, researchers can test various hypotheses about the nature of vacuum fluctuations, field interactions, and potential deviations from standard models. The effect has become a kind of laboratory window into the subtle architecture of quantum space. Interestingly, the Casimir effect is not limited to electromagnetic fields. In principle, any quantized field that responds to boundary conditions could produce a similar phenomenon. The same mechanism, restriction of allowed field modes due to geometric constraints, applies to scalar fields, fermionic fields, and hypothetical particles that have yet to be observed. This universality makes the Casimir effect not just a peculiarity of electromagnetism, but a fundamental feature of quantum fields in confined spaces. On a more practical level, the Casimir force has implications for emerging technologies, particularly in the realm of micro and nano electromechanical systems. At such small scales, where components may be only hundreds of nanometers apart, the Casimir force can dominate over other forces like gravity or even electrostatics. This can lead to unintended consequences, such as stiction, where tiny machine parts stick together due to vacuum-induced attraction. Understanding and mitigating these effects is essential for the development of more reliable nanoscale devices. Researchers have even explored ways to manipulate the Casimir force, turning it from attractive to repulsive by changing the materials or the intervening medium between the plates. Although the effect is subtle and difficult to reverse, the ability to engineer Casimir forces opens the door to novel applications, such as frictionless surfaces, energy-efficient actuators, and quantum-scale mechanical controls. These technologies are still in their infancy, but they underscore how the strange behaviors of the vacuum may be harnessed in the future, not just studied. There is also an intriguing theoretical connection between the Casimir effect and the concept of vacuum energy on cosmological scales. If the vacuum between two plates can produce a measurable pressure due to suppressed modes, then it's natural to wonder how vacuum energy behaves in the vast, unconstrained expanse of the universe. This question touches directly on the cosmological constant problem. The discrepancy between the vacuum energy predicted by quantum field theory and the dark energy inferred from cosmic expansion. The Casimir effect doesn't solve this problem, but it provides a laboratory-scale analogy that illustrates the sensitivity of vacuum energy to boundary conditions and geometry. Indeed, some physicists have speculated whether the shape of the universe or the presence of cosmic-scale boundaries might alter the behavior of vacuum energy in ways we do not yet understand. While these ideas remain speculative, they highlight how phenomena first observed in carefully controlled laboratory settings can resonate with the deepest questions in cosmology. Despite the remarkable clarity of the Casimir effect as a prediction of quantum theory, its conceptual implications continue to provoke debate and wonder. One point of contention is whether the energy involved in the Casimir force is truly from the vacuum, or a result of the interaction between matter and field. Some interpretations frame the effect as a shift in the ground state energy of the electromagnetic field due to boundary conditions, while others treat it as arising from the field's response to the presence of the conductors. Both views are mathematically equivalent, but they reflect different intuitions about where the source of the force lies. This ambiguity is characteristic of quantum field theory as a whole. The language we use, virtual particles, zero-point energy, vacuum fluctuations, is helpful, but it often masks deeper complexities. The Casimir effect teaches us that these conceptual tools, while not directly observable, can produce physical outcomes with precision and predictability. It reminds us that quantum fields are not abstract fictions but active components of reality. It also invites us to rethink the idea of space itself. If space can produce pressure in the absence of matter or heat, then it is not merely a passive container. It is not an inert backdrop upon which events unfold. Rather, it is an active medium, alive with fluctuations, sensitive to geometry, and capable of exerting influence. What we call nothing is not neutral. It is not powerless. It has structure, and under the right conditions, it has force. The Casimir effect reveals this in the most tangible way. It shows us that even in silence, there is pressure. Even in emptiness, there is presence. And perhaps as we look deeper into the layers of reality, we will find that the most enduring truths do not emerge from what is seen, but from what quietly shapes the space between things. The vacuum, once thought to be the absence of everything, may turn out to be the origin of everything instead. Chapter 4. Zero-point energy. The lowest you can go isn't zero. In classical physics, there is a reassuring certainty in the idea that when something stops moving, its energy is zero. This makes intuitive sense. A pendulum at rest, a cooled-down gas, a motionless particle, all are said to be in their lowest energy states, devoid of motion, devoid of energy. But in quantum mechanics, this notion breaks down. Even at absolute zero, when all classical thermal motion has ceased, there remains a persistent, irreducible energy. This is zero-point energy, the lowest possible energy that a quantum system can possess. It cannot be removed, cannot be dissipated, and cannot be turned off. It is a fundamental feature of the quantum world, built into the very structure of nature. The term zero point comes from the idea that this energy exists at the 0 point of a system's potential, when no classical energy remains. But despite the name, it does not imply zero energy. In fact, it implies quite the opposite, that even when all measurable motion disappears, the system retains a baseline of quantum activity. This energy is not the result of external input, nor is it a consequence of hidden motion. It is embedded in the mathematics of quantum theory itself. To see why this is the case, one must understand how quantum systems behave fundamentally differently from classical ones. In classical physics, a harmonic oscillator, like a spring or a mass on a pendulum, can be brought to complete rest. At its minimum energy, it stops. But in quantum mechanics, every oscillator, even in its ground state, continues to fluctuate. These fluctuations are not due to noise or imprecision. They are a reflection of the uncertainty principle. A particle cannot have both a perfectly defined position and momentum. If you try to pin down its location, its momentum becomes uncertain, and vice versa. The result is a perpetual, unavoidable jitter, the zero-point motion that ensures the particle is never truly at rest. This principle applies not only to simple systems like particles in a box or atoms in a trap. It applies to all quantum fields, including the electromagnetic field, the electron field, and every other field that defines the fundamental particles of nature. These fields are made up of countless quantum harmonic oscillators at every point in space. Each one of them, even in its ground state, contributes a small amount of energy. When you sum these contributions across the vast fabric of space, you obtain a vacuum that is anything but empty. This ground state energy is what we refer to as the zero-point energy of the vacuum. It exists not just in theoretical descriptions, but manifests in physical phenomena. In previous chapters, we've seen how this energy helps explain atomic behavior and contributes to measurable forces like the Casimir effect. But the implications of zero-point energy stretch far beyond the laboratory. They influence the structure of atoms, the propagation of fields, and potentially the evolution of the entire universe. One compelling example comes from molecular physics. The vibrational states of molecules are quantized, and even in the lowest state, where classically the atoms should be motionless, the molecule continues to vibrate due to zero-point motion. This energy affects the molecule's size, its chemical behavior, and its interactions with other molecules. Without zero-point energy, matter as we know it would not behave the way it does. Chemical bonds would be weaker, atomic structures would collapse differently, and the properties of solids and liquids would shift in unpredictable ways. The effects of zero-point energy also appear in superconductors and superfluids, where quantum coherence extends over macroscopic distances. In these systems, particles act not as isolated individuals, but as coordinated ensembles, moving in unison under the influence of quantum rules. Even at temperatures near absolute zero, where thermal motion is minimal, these systems retain dynamic behaviors, flows, oscillations, and phase transitions that are driven in part by zero-point fluctuations. In quantum optics, the concept of zero-point energy plays a key role in spontaneous emission. An excited atom in a vacuum does not wait indefinitely to release its energy. Even in perfect darkness, it emits a photon and returns to its ground state. This emission is stimulated by the vacuum fluctuations, the ever-present zero-point energy of the electromagnetic field. Without this baseline activity, atoms might remain excited forever, violating the stability of matter and disrupting the flow of energy through the universe. The reality of zero-point energy poses a challenge when we try to reconcile it with general relativity. If every point in space contains a small amount of energy, and these contributions add up over cosmological distances, the result is a colossal vacuum energy density. Theoretical estimates, based on quantum field theory, predict an energy density that is orders of magnitude larger than what we observe in the cosmos. This is the so-called vacuum catastrophe, a discrepancy of more than 100 orders of magnitude between the predicted vacuum energy and the observed value of the cosmological constant. Such a vast mismatch is not just a mathematical curiosity. It threatens the coherence of modern physics. If the vacuum really held that much energy, the universe would have curled in on itself or expanded explosively long ago. That it hasn't suggests that something is missing in our understanding. Perhaps some unknown mechanism cancels out most of the zero-point energy, or perhaps our calculations are incomplete. It remains one of the deepest open questions in physics. Some theorists have explored whether zero-point energy could be tapped or harnessed as a source of power. The idea has appeared in speculative science and even science fiction. Engines powered by the vacuum, devices that draw energy from the very fabric of space. But these ideas, while intriguing, are not supported by mainstream physics. The zero-point energy is not free for the taking. It represents the minimum energy of a quantum system, the baseline below which you cannot go. Extracting usable work from it would violate fundamental thermodynamic principles, and no experimental evidence has ever shown a method for doing so. Nonetheless, the question persists, and some experimentalists have looked for subtle ways to influence or modulate the effects of zero-point energy. Tiny changes in geometry, boundary conditions, or material properties might shift how the vacuum behaves in specific regions. These studies are ongoing, and while they haven't produced practical devices, they do provide deeper insights into how the vacuum interacts with matter and fields. Zero-point energy is not just an abstract curiosity. It is a structural component of physical law. It is woven into every quantum system, from the smallest atoms to the largest cosmic fields. It sets the tone for all higher energy states, defining a universal baseline. And while we cannot see it directly, its fingerprints are everywhere. In the behavior of light, the structure of molecules, and the quiet pull of unobservable forces. Unlike energy we generate or consume, zero-point energy cannot be reduced or removed. It does not fuel machines or radiate heat. It simply is, a constant hum beneath reality, a presence that marks the line between what is and what cannot be. And yet, for all its certainty, we do not fully understand why it exists. We can calculate it, observe its consequences, and use it in equations, but the deeper meaning remains elusive. Is it a mathematical necessity, a feature of deeper physical laws not yet discovered, or a remnant of a more fundamental structure that predates our current models? Perhaps zero-point energy represents a kind of cosmic memory, a reminder that stillness is never truly still, that even in perfect calm, there is motion, that the universe at its quietest is never silent. In a way, it invites us to reflect on our own sense of quietness. When we sit in silence, we imagine we are at rest. But beneath that silence, our bodies hum with life, our cells vibrate, our thoughts shift. Our molecules, even at the lowest temperatures, tremble with quantum motion. We are, at every level, alive with zero-point energy. Even the universe, sprawling, expanding, and ancient, retains that quiet hum. It is the breath between the stars, the motion between thoughts. The lowest you can go isn't zero, because in the quantum world, even nothing must be something. Chapter 5. Spontaneous Emission: How Nothing Makes Atoms Glow. At first glance, spontaneous emission seems paradoxical. It suggests that something, light, energy, action, can emerge from nothing. In the case of atoms, it means that even in a perfect vacuum, devoid of photons or thermal radiation, an excited atom will eventually release its energy by emitting a photon. It does not need to be triggered by external radiation or collision. it simply lets go. And this letting go, this act of emission, is not just a curious quirk. It is a window into the deep interaction between matter and the quantum vacuum. In classical electrodynamics, light emission requires a cause. A charged particle must be accelerated to generate electromagnetic radiation. An antenna must oscillate. A spark must occur. Nothing happens unless something is done to disturb the system. But in quantum mechanics, atoms can change state on their own without an external push. An electron in an excited state does not need to be jostled. It can spontaneously fall to a lower energy level and release a photon, even when no light or field is present around it. The question is, what prompts the emission? The answer lies in the nature of the vacuum. As established in earlier discussions, the vacuum in quantum theory is not empty. It is filled with fluctuations, restless, omnipresent, and unavoidable. These fluctuations are not just abstract constructs. They manifest as temporary excitations of the electromagnetic field, constantly flickering in and out of existence. Although they are not detectable as real photons, they act as a background field, capable of interacting with matter. When an atom is in an excited state, it represents a configuration that is not in its lowest possible energy. The system is unstable, even if only subtly. Classically, it might remain in this state forever unless perturbed. But quantum mechanically, the atom is embedded in a background of zero-point fluctuations. These fluctuations couple to the atom's internal degrees of freedom, the arrangement of its electrons, the structure of its energy levels, and induce transitions between states. In this way, spontaneous emission can be seen as an interaction between the atom and the vacuum field. The vacuum provides the stimulus, however faint, that nudges the atom toward stability. The process is not forced in the way classical physics would require, but emerges probabilistically from the structure of quantum field interactions. The photon that is emitted is real. It carries energy, it travels outward, and it can be detected. But the cause of its creation is not a visible actor. It is the invisible sea of vacuum fluctuations. This understanding of spontaneous emission was formalized through quantum electrodynamics, particularly through the work of Dirac, Fermi, and others in the early 20th century. By treating the electromagnetic field as quantized, broken down into discrete modes that obey the rules of quantum mechanics, physicists could describe light not as a continuous wave, but as a collection of photons. Each mode of the field could absorb or emit photons, and each atom could couple to these modes depending on its configuration. In this framework, spontaneous emission arises from the vacuum expectation value of the field operators. That is, even in the ground state of the field, there is a non-zero probability for the field to interact with the atom. This subtle interaction changes the dynamics of the system, introducing a finite lifetime for excited states. Without the vacuum, there would be no decay. The atom would remain excited, frozen in a metastable configuration. It is the vacuum that introduces the possibility of change. This idea challenges traditional notions of causality. How can a system decay without a cause? In quantum theory, cause and effect are often statistical. The emission is not deterministic but probabilistic. Over time, the likelihood of emission increases, but no external signal determines exactly when it occurs. The vacuum, present but unseen, defines the conditions under which the atom may act, but does not dictate the timing. Experimentally, spontaneous emission is a well-established phenomenon. It defines the basic behavior of atoms and molecules and underlies many technologies, from lasers to fluorescent lights. When you see a glowing neon sign, the light it emits is largely a result of spontaneous transitions between atomic states. The photon released in each case was not pushed into being by external light, but emerged from the quantum dynamics of the system in contact with the vacuum. Despite its ubiquity, spontaneous emission is not immutable. It can be altered by changing the environment around the atom. One of the most striking demonstrations of this is the Purcell effect, where placing an atom in a resonant cavity can dramatically change its emission rate. The reason is that the cavity modifies the vacuum field modes available to the atom. If the cavity enhances certain modes, specific frequencies of the electromagnetic field, then the atom couples more strongly to them and decays faster. If it suppresses the modes, the decay can slow down. In extreme cases, it can be nearly halted. This controllability is both a confirmation of the quantum theory and a gateway to new technologies. Quantum optics and cavity quantum electrodynamics exploit these principles to build highly coherent light sources, manipulate quantum bits in quantum computers, and create entangled photon states for quantum communication. All of these rely on a deep understanding of how atoms emit and how the vacuum shapes that emission. Another realm where spontaneous emission plays a crucial role is in astrophysics. The light we receive from distant stars and galaxies often includes spectral lines, specific frequencies of radiation that correspond to atomic transitions. These lines bear the fingerprints of the atoms that produced them and allow scientists to determine the composition, temperature, and motion of celestial objects. The fact that these transitions occur even in the vacuum of space is a direct consequence of spontaneous emission. The photons travel for light years across the emptiness between stars and still carry the encoded memory of an atom's moment of release. Beyond technical applications and observational consequences, spontaneous emission offers a philosophical lesson. It reveals that emptiness is never truly passive, that absence of matter does not mean absence of action. The vacuum, though invisible, is constantly engaged in shaping the behavior of the universe. It makes decay possible. It allows light to be born from isolated atoms. It sustains the flow of time by providing the background against which unstable systems evolve. One might expect that in the quietest possible environment, nothing would happen. But in quantum physics, quiet does not mean stillness. Even the most isolated systems are connected to the vacuum, and through that connection, to all of reality. There is no absolute solitude. Every atom, every particle, every excitation is in dialogue with the vacuum field, even when no one else is around to listen. This has implications for how we understand isolation, change, and causality itself. Spontaneous emission shows that the universe does not require external permission to evolve. That processes can begin without being pushed. That the conditions of being are enough to generate becoming. The vacuum does not force emission, but it permits it. And in that permission lies the potential for creation. As with other phenomena rooted in quantum fields, spontaneous emission blurs the line between presence and absence. It reminds us that silence is filled with whispers, that stillness is animated by possibility, and that even in the absence of all visible influence, the universe moves forward. Perhaps that is true not just for atoms, but for us. That change can arise not only from what we do, but from the space around us. That growth does not always require pressure or instruction, but can be born from the invisible conditions that surround us, quietly inviting us to become. Chapter 6. Vacuum polarization, when empty space bends around charges. In the classical view of physics, the vacuum is passive. It plays no active role in physical interactions and simply serves as the backdrop against which forces play out. A charged particle, for example, is said to generate an electric field that extends out through space, affecting other charges that enter that region. But space itself, in the classical sense, remains unchanged. It transmits the field but does not respond to it. This picture begins to dissolve when quantum mechanics enters the equation. In the quantum world, even the vacuum becomes a participant. It responds, it shifts, and it rearranges itself in the presence of a charge. This phenomenon is known as vacuum polarization. Vacuum polarization refers to the alteration of the vacuum due to the presence of an electric charge. In quantum electrodynamics, the vacuum is not an inert emptiness, but a medium filled with fluctuating fields and virtual particles. These virtual particles include electron-positron pairs, which momentarily spring into existence due to energy-time uncertainty and just as quickly annihilate each other. Although these pairs cannot be observed directly, their effects are measurable and real. When a charge is introduced into this environment, it influences the behavior of these fluctuations. The virtual particles respond to the electric field, aligning in a way that mimics the behavior of a dielectric material in classical physics. In a conventional dielectric, placing a positive charge near a medium causes negative charges in the material to shift slightly toward it, while positive charges shift slightly away. This redistribution of charge partially cancels the original field, leading to a screened or reduced effective charge at larger distances. A similar process occurs in the quantum vacuum. The virtual electron-positron pairs become polarized by the presence of a real charge. The virtual electrons are drawn toward the positive charge, while the virtual positrons are pushed away. Although these particles do not persist long enough to be called real, their transient polarization distorts the vacuum and alters the effective strength of the electric field. This distortion has measurable consequences. One of the clearest manifestations is a correction to the strength of the electromagnetic interaction, especially at short distances. When probing very close to a charged particle, on subatomic scales, the shielding effect of vacuum polarization diminishes, and the effective charge appears larger. This behavior has been confirmed through high-precision experiments, such as those involving the hydrogen atom. One notable outcome is the Lamb shift, a tiny change in the energy levels of electrons and hydrogen due to interactions with the vacuum. Though first observed in the 1940s, the shift remains a cornerstone example of how quantum fluctuations influence atomic structure. Vacuum polarization also plays a role in scattering processes involving high-energy particles. When two particles interact via the exchange of virtual photons, the vacuum around them modifies the properties of those photons. The effective coupling between the particles depends on the energy scale of the interaction, which determines how much the vacuum polarization contributes. This energy dependence gives rise to what is called the running of the fine structure constant, a fundamental number that governs the strength of electromagnetic interactions. At higher energies, the constant increases slightly, reflecting the reduced shielding effect at smaller distances. These effects are not merely theoretical predictions. They have been verified with extraordinary precision in experiments involving particle accelerators and atomic clocks. The quantum corrections due to vacuum polarization must be accounted for to match observations with theory, often down to parts per billion. Without them, the predictions of quantum electrodynamics would fail to align with the behavior of nature. This agreement between theory and measurement is one of the triumphs of modern physics and a testament to the reality of the vacuum structure. Importantly, vacuum polarization is not unique to the electromagnetic field. In principle, similar effects occur for any quantum field that couples to matter. In quantum chromodynamics, for instance, the vacuum responds to the presence of color charge in a highly nonlinear way, leading to the phenomenon of color confinement. While the details are more complex than in electrodynamics, the underlying idea remains the same. The vacuum is reactive. It bends around sources of influence. There is also a deep symmetry at play. The polarization of the vacuum is not a violation of any conservation law. The transient virtual pairs that shift under the influence of a charge still obey the rules of quantum mechanics. They appear and disappear without violating energy conservation, thanks to the allowance for uncertainty over very short timescales. Their effects, while fleeting, accumulate into lasting changes in how fields propagate and how particles interact. The vacuum, in this sense, is like a fluid medium that remembers the presence of charge even after the direct influence has passed. Vacuum polarization has been proposed as a tool for probing new physics beyond the standard model. Since the vacuum interacts with fields of all known particles, it could, in principle, also respond to unknown fields, those associated with dark matter or hypothetical new forces. Experiments searching for deviations in the polarization of light traveling through strong magnetic fields or in the behavior of particles in high-intensity lasers are in part motivated by the hope of detecting such deviations. Any unexpected polarization effects could signal the presence of new virtual particles, modifying the vacuum's behavior in ways not yet understood. One area where vacuum polarization intersects with general relativity is in the study of curved spacetime. In a gravitational field, the vacuum fluctuations themselves can be altered by the curvature of spacetime. This suggests that vacuum polarization could be influenced not only by charges and fields, but also by gravity. Although the full unification of quantum field theory and gravity remains elusive, certain semi-classical calculations show that the energy and momentum of the polarized vacuum can contribute to the curvature of spacetime, albeit in subtle ways. This has implications for black holes, cosmological inflation, and possibly the behavior of the early universe. At the edge of experimental capability, researchers are exploring the nonlinear behavior of the quantum vacuum under extreme conditions. According to theory, in the presence of an extraordinarily strong electric or magnetic field, the vacuum could become polarized to such an extent that it behaves like a birefringent medium, a material that bends light differently depending on its polarization. This phenomenon, known as vacuum birefringence, is predicted by quantum electrodynamics, but has not yet been directly observed. Experiments using powerful laser systems are ongoing, aiming to detect this subtle optical signature. Although the effect is tiny, its detection would mark a new chapter in our understanding of how light and vacuum interact. It would demonstrate in an even more direct way that the vacuum is not a neutral, invisible backdrop, but a participant in the drama of physical law. A medium that can be stretched, bent, and polarized, even in the absence of matter. In this picture, the vacuum becomes something more than a stage. It becomes an actor, responsive, dynamic, and deeply intertwined with the forces of nature. The notion that a charged particle affects not only its surroundings but the fabric of space itself challenges our deepest intuitions. It reminds us that the lines we draw between substance and emptiness, between presence and absence, are often blurred in the quantum world. And while the vacuum's polarization might seem like a technical detail, it represents a profound shift in how we view the universe. Forces are not just transmitted across emptiness, they are shaped by it. The vacuum does not merely allow interaction. It molds interaction, softens it, sharpens it, and sometimes hides it. There is a quiet poetry in this responsiveness, a kind of memory built into space, an imprint of every particle, every field, recorded not in marks or scars, but in subtle distortions that ripple through the invisible sea beneath us. Perhaps the universe, at its core, is not empty after all. Perhaps it is a mirror that bends around us, shaped by every presence, every motion, every breath. And perhaps the vacuum itself is not what remains when all else is gone, but what is always there, bending, adapting, waiting. Chapter 7. Particle Creation in Curved Spacetime. In the framework of quantum field theory, particles are no longer considered fundamental objects, but rather as excitations of underlying fields that pervade space. These fields are omnipresent, rippling quietly even in the absence of apparent matter or motion. In the flat, inert vacuum of empty spacetime, the ground state of these fields appears stable and unchanging. But when spacetime itself becomes dynamic, when it bends, stretches, or accelerates, the nature of that vacuum changes. In such conditions, Even a field in its lowest energy state can begin to spawn particles. This phenomenon, known as particle creation in curved spacetime, reveals that the boundary between something and nothing is not absolute. It depends on geometry, on motion, and on perspective. One of the most profound lessons of general relativity is that gravity is not a force in the traditional sense, but a manifestation of curved spacetime. Massive objects warp the geometry around them, and this curvature dictates how matter moves. When this curvature becomes dynamic, as in the case of expanding universes, collapsing stars, or rotating black holes, the fabric of spacetime becomes a changing stage for quantum fields. Unlike in classical physics, where a field's lowest energy state is unaffected by the coordinates used to describe it, in quantum field theory, the vacuum is not invariant under all transformations. Different observers moving differently or existing in differently curved regions can disagree about what counts as a particle, or even whether particles are present at all. This ambiguity lies at the heart of particle creation in curved spacetime. In a static, flat universe, the vacuum is uniquely defined. There is a clear notion of what it means for a field to be in its ground state. But in an expanding or contracting universe, or near a strong gravitational field, this clarity dissolves. The vacuum becomes observer-dependent. A field that appears empty to one observer may appear filled with particles to another. This realization was first articulated in rigorous terms during the study of cosmological inflation and black hole thermodynamics, but its implications stretch across modern theoretical physics. Perhaps the most striking example is Hawking radiation, the prediction that black holes are not completely black, but instead emit radiation due to quantum effects near their event horizons. Stephen Hawking's seminal work in the 1970s demonstrated that the curvature of spacetime near a black hole can lead to the creation of real particles that escape to infinity, even though the region outside the black hole is otherwise vacuum. This process is subtle. It does not involve particles tunneling out of the black hole or being ejected by a physical mechanism. Instead, it emerges from the mathematical structure of quantum fields in curved spacetime. The key insight is that near the event horizon, the separation between different regions of space leads to a mismatch between the vacuum states perceived by distant observers and those near the horizon. In a simplified picture, pairs of virtual particles constantly form and annihilate near the horizon, as they do everywhere in the vacuum. Occasionally, due to the extreme curvature, one member of the pair falls into the black hole while the other escapes. The escaping particle becomes real, observable radiation, while the infalling one contributes negative energy to the black hole, slowly reducing its mass. Though this description is heuristic, it captures the essence of the process. Particle creation not from material interactions, but from the structure of spacetime itself. Hawking radiation is a consequence of the fact that quantum fields respond differently to curved geometries. What we perceive as particle production is actually a change in the quantum state of the field, triggered by the gravitational environment. This insight revolutionized how physicists view black holes, leading to the idea that they are thermodynamic objects with entropy and temperature. A black hole, once thought to be a final, unchanging state, now appears as a dynamic system that can radiate, evolve, and ultimately evaporate. But particle creation is not limited to black holes. It also occurs in expanding universes, such as our own. During the early moments of cosmic inflation, the rapid expansion of space stretched quantum fluctuations to cosmological scales. These fluctuations, originally microscopic and quantum in nature, became classical as they were stretched beyond the horizon of causal contact. The result was a spectrum of primordial density perturbations, tiny variations in energy density that would later grow into galaxies, clusters, and the large-scale structure of the universe. This process, sometimes called cosmological particle production, reveals that the seeds of all cosmic structure were planted by the stretching of vacuum fluctuations in a curved, expanding spacetime. The inflationary epoch transformed the vacuum into matter, not in a metaphorical sense, but in a calculable, testable way. The patterns of temperature variations in the cosmic microwave background, observed by satellites like COBE, WMAP, and Planck, reflect these early quantum fluctuations. The geometry of spacetime gave birth to the architecture of the cosmos. Even in less extreme settings, curved spacetime can affect particle perception. The Unruh effect, for instance, demonstrates that an accelerating observer in flat spacetime will perceive a thermal bath of particles, even though an inertial observer perceives a vacuum. This suggests that the notion of a vacuum is relative, not to the field itself, but to the observer's trajectory through spacetime. The uniformly accelerating detector will register clicks, indicating the detection of particles, while a stationary detector will remain silent. Both are correct in their own frames. The difference lies not in the field, but in the experience of the field through motion. These ideas challenge classical intuitions. They suggest that what we call a particle is not an absolute entity, but a feature of a quantum field as seen from a particular frame of reference. This relational aspect of particle definition is fundamental to quantum field theory in curved spacetime. It implies that the vacuum is not a static object, but a dynamic participant shaped by geometry, motion, and perspective. These phenomena also raise deeper questions about the unity of physics. In standard quantum field theory, defined on a flat background, calculations proceed with great precision. But when gravity is included, when space-time itself becomes a quantum variable, this precision breaks down. Quantum field theory in curved space-time is an effective theory, a way to apply quantum principles to classical gravitational backgrounds. But it is not a complete theory of quantum gravity. It describes how matter responds to curved spacetime, but not how spacetime itself becomes quantized. Attempts to go further, to build a full theory of quantum gravity, often start from the insights provided by particle creation in curved spacetime. The thermal nature of black holes, the entropy associated with event horizons, the observer dependence of vacuum states, all point to a deeper structure that lies beneath both general relativity and quantum field theory. The idea that spacetime itself may be emergent, arising from more fundamental quantum information, is gaining traction in theoretical circles. Particle creation in curved backgrounds is one of the phenomena guiding this shift in thinking. Despite its abstract nature, the concept has real consequences. The idea that the vacuum can be unstable in curved spacetime leads to theoretical possibilities like vacuum decay, where our current vacuum could tunnel into a lower energy state triggered by fluctuations in geometry. Though this scenario is highly speculative and has no empirical support, it remains a mathematical possibility in certain field theories. Even more concretely, the behavior of quantum fields in the early universe provides a mechanism for baryogenesis, the creation of the matter-antimatter asymmetry, and for the generation of cosmic magnetic fields. These processes depend on how fields interact with time-dependent backgrounds, and on how curvature can act as a catalyst for transitions that would not occur in flat spacetime. In essence, curved spacetime gives the vacuum a voice. It allows the quiet fluctuations of fields to become real, observable phenomena. It creates particles from geometry, structure from distortion, presence from curvature. The vacuum, shaped by spacetime, becomes an engine for creation. It is a humbling idea that the very fabric of space, when disturbed, can give rise to matter and energy. That the empty background is not empty at all, but brimming with potential, waiting for the universe to bend just enough to release it. And that what we call nothing is only a placeholder for the things we do not yet know how to see. Perhaps we, too, are like those particles, emerging from the subtle shape of something deeper, carried by a curvature we do not yet understand. Arising not from matter alone, but from structure, from motion, from the quiet ripple of something more fundamental than space or time. Chapter 8. The Quantum Vacuum and Dark Energy. For much of the 20th century, cosmologists believed the universe's expansion, initiated by the Big Bang, was gradually slowing down. Gravity, they reasoned, must be pulling back on the galaxies, decelerating their outward motion. But in 1998, observations of distant supernovae revealed something astonishing. Instead of decelerating, the expansion of the universe was accelerating. Galaxies were not just moving apart, they were doing so faster over time. The cause of this acceleration was attributed to something entirely unexpected: a repulsive component of the universe's energy budget, now referred to as dark energy. Dark energy makes up approximately 70% of the total energy density of the universe, and yet it remains among the most enigmatic entities in modern physics. It appears to be uniform in space, constant in time, and does not clump or cluster like matter. Its only apparent effect is to accelerate the expansion of spacetime itself. And while several models have been proposed to explain it, the most natural, though also the most troubling, comes from quantum field theory. That model points directly to the quantum vacuum. In the quantum field theoretical view, the vacuum is not empty. It is filled with fluctuating fields, each contributing a small amount of energy even in their lowest possible states. These zero-point energies are not artifacts of poor measurement or misunderstanding. They are required by the mathematical structure of quantum mechanics. Every field, whether scalar, vector, or fermionic, has a ground state that carries residual energy. When we sum the zero-point energies of all known quantum fields across all possible modes, the result is a vacuum energy density of staggering magnitude. But herein lies the problem. The predicted vacuum energy from quantum field theory is about 120 orders of magnitude larger than the observed value inferred from cosmological acceleration. That is not a small discrepancy. It is, by many measures, the largest known mismatch between theory and observation in all of science. This conundrum is often referred to as the cosmological constant problem, named after the term Einstein once introduced and later rejected in his equations of general relativity to allow for a static universe. In Einstein's original formulation, the cosmological constant acted as a repulsive force that countered gravity. When he discovered the universe was expanding, he called the constant his greatest blunder. But with the discovery of cosmic acceleration, the cosmological constant returned, not as a mistake, but as a potential clue. If dark energy is equivalent to a cosmological constant, then it acts uniformly across all of space, exerting negative pressure and driving the expansion of the universe outward. The form of this energy is precisely what quantum field theory predicts in the form of vacuum energy, and yet the magnitude is drastically off. This raises one of the most profound and unresolved questions in physics. Why is the vacuum energy so small, but not zero? If some mechanism exists to cancel the immense contributions from quantum fluctuations, why does it not cancel them entirely? Why is there just enough leftover energy to accelerate the cosmos, but not enough to disrupt the formation of galaxies and stars? The answer remains elusive. Some theoretical physicists speculate that a symmetry, yet undiscovered, might suppress the vacuum energy. Others propose that the observed value is anthropic, that in a multiverse of possible vacuum states, we happen to live in one where the vacuum energy is small enough to permit complex structures to form. This line of reasoning suggests that in most universes, vacuum energy is too large, causing rapid expansion or collapse. Life, and observers like us, could only arise in the rare sliver of the multiverse where vacuum energy is fine-tuned to a usable level. While the anthropic argument is controversial, It highlights the strange coincidence between the scale of dark energy and the requirements for cosmic habitability. Another possibility is that what we call dark energy is not a true cosmological constant, but a dynamic field, an evolving energy component with properties that change over time. This hypothetical substance is often referred to as quintessence. Unlike vacuum energy, which is constant, quintessence could fluctuate or decay, leading to subtle variations in cosmic acceleration over billions of years. Current observations are consistent with both models, but not precise enough to distinguish between them. Ongoing and future missions, such as Euclid and the Nancy Grace Roman Space Telescope, aim to map cosmic expansion with unprecedented accuracy in hopes of narrowing down the possibilities. If dark energy is indeed tied to vacuum energy, then it represents not just a cosmological phenomenon, but a deep connection between quantum theory and general relativity. It becomes a bridge between the very small and the very large, between fluctuations at the Planck scale and the stretching of spacetime across billions of light years. This unity, if confirmed, would provide a glimpse of the long-sought quantum theory of gravity, one that we do not yet possess, but toward which these mysteries gently guide us. There is also the question of the vacuum's contribution to the energy-momentum tensor in general relativity. According to the theory, energy and momentum curve spacetime. Vacuum energy, despite its uniformity, carries pressure, specifically negative pressure. This exotic property leads to repulsion rather than attraction. While normal matter collapses under gravity, vacuum energy causes space to expand. This is not an optional feature. It arises directly from how energy density and pressure source curvature in Einstein's field equations. In effect, vacuum energy is gravitationally active. It has real influence on the geometry of the universe. Interestingly, vacuum energy may have played a pivotal role in the very early universe. During the inflationary epoch, a brief period of exponential expansion thought to have occurred a fraction of a second after the Big Bang, a form of vacuum-like energy drove the universe to balloon in size by many orders of magnitude. This process flattened spacetime, diluted defects, and seeded the initial density fluctuations that grew into cosmic structure. While this early inflationary vacuum energy is not the same as the dark energy we observe today, it suggests a broader principle, that the vacuum can change, and that these changes have epoch-defining consequences. This raises the speculative but fascinating idea that the vacuum itself may not be eternal. It may undergo transitions, shifting from one configuration to another. In some quantum field theories, our vacuum is only metastable, not the lowest possible energy state, but a local minimum. If a lower energy vacuum exists, it could one day be reached via quantum tunneling, initiating a phase transition that would fundamentally alter the laws of physics. This hypothetical vacuum decay would propagate outward at the speed of light, rewriting reality in its wake. There would be no warning and no way to see it coming. While current measurements suggest that our vacuum is stable on cosmological timescales, the very fact that such a possibility exists reveals the profound implications of vacuum energy for the fate of the universe. Still, much remains unknown. Is the vacuum energy truly constant, or is it an evolving field? Does it originate from quantum fluctuations, or from an entirely different source yet to be uncovered? Is its magnitude set by chance, by necessity, or by deeper principles beyond our current grasp? Each of these questions touches not just on cosmology, but on the foundations of physics itself. What makes the puzzle even more poignant is that the effects of dark energy are silent. We do not feel the expansion. We do not see the vacuum's pressure. There are no sounds, no signs, yet its influence pervades every corner of the cosmos. It stretches the fabric of space, speeds the retreat of distant galaxies, and shapes the future evolution of everything. Slowly, invisibly, it is driving the universe toward a colder, emptier fate. If dark energy remains constant, the universe will continue to expand forever. Over time, galaxies will drift out of sight, stars will burn out, and black holes will evaporate. The cosmos will become increasingly dilute, increasingly still, a heat death driven not by fire, but by the quiet, relentless push of the vacuum. This future is not dramatic, but it is absolute. And it is being orchestrated invisibly by the same quantum fluctuations that underlie all matter and energy. The vacuum, once thought to be the absence of all things, now appears to hold the keys to the universe's expansion, its origin, and its ultimate fate. It is a reservoir not of emptiness, but of hidden influence, a silent architect of cosmic history. And perhaps in its quiet persistence there is something to contemplate, that the most powerful force in the universe is not violent or sudden. It is subtle, gentle, patient, a pressure that does not shout but endures. Not a storm, but a breath that expands forever. Chapter 9. Harnessing the Quantum Vacuum, Science Fiction or the Next Revolution. Among the many revelations of quantum physics, perhaps none is more simultaneously profound and tantalizing than the discovery that the vacuum is not empty. As discussed throughout this journey, the vacuum teems with quantum fluctuations, virtual particles, and irreducible energy. It influences the motion of particles, the structure of atoms, and even the expansion of the universe. But beyond its role in shaping physical law, the quantum vacuum raises a provocative question. Can it be harnessed? The idea of extracting usable energy from the vacuum has long fascinated physicists, engineers, and visionaries alike. The prospect is seductive, an inexhaustible energy source permeating all of space, operating continuously at all scales, available wherever one might be. No fuels to burn, no mass to convert, no input required, just the ambient, invisible fabric of the universe itself. At the heart of this idea is zero-point energy, the residual energy retained by quantum systems even in their ground states. In quantum field theory, every mode of every field contributes a small amount of this energy, and when summed across the infinite spectrum of frequencies, the total becomes vast. But this vastness is largely theoretical, and therein lies the challenge. Despite its conceptual magnitude, the vacuum's energy is not something that can be extracted in the usual sense. It is the lowest possible energy a system can have, the baseline from which all physical activity is measured. Trying to take energy from the vacuum is, in most formulations, equivalent to trying to drop below absolute zero. Nevertheless, that has not stopped people from trying, or from imagining the possibilities. The concept of vacuum energy extraction appears frequently in speculative technologies, especially within the realm of science fiction. Stories of spacecraft powered by zero-point reactors, cities lit by the energy of empty space, or engines that generate thrust without propellant all find their roots, however loosely, in the science of the vacuum. Some of these concepts draw on real effects, such as the Casimir effect, which demonstrates that vacuum fluctuations can exert measurable forces. Others extrapolate more freely, invoking mechanisms not currently supported by mainstream physics. One of the most famous speculative devices was the so-called EM drive, which claimed to produce thrust without ejecting mass. The mechanism was said to exploit the properties of the vacuum or resonant electromagnetic cavities to generate momentum. Early tests reported small forces, but later, more rigorous investigations failed to reproduce the effect under controlled conditions. As of now, the EM drive is considered a cautionary example of experimental error and wishful thinking. While it captured public imagination, it ultimately underscored the importance of precision and skepticism when dealing with extraordinary claims. Other concepts attempt to exploit quantum fluctuations through more grounded approaches. For example, researchers have investigated whether the Casimir effect could be harnessed in micro and nano electromechanical systems. At such small scales, where Casimir forces become non-negligible, It is conceivable to design devices that use vacuum-induced pressure to perform useful work. But even here, there are fundamental limitations. The energy required to reset or cycle these systems often exceeds the energy extracted. Conservation laws remain intact. The second law of thermodynamics does not yield. Some approaches consider dynamic Casimir effects, where motion or time-dependent boundary conditions induce the emission of real photons from the vacuum. This has been observed in superconducting circuits, where rapidly modulating the properties of a quantum system can lead to photon creation. While intriguing, these processes require significant external energy input to manipulate the boundaries or oscillators involved. Thus, the energy emitted ultimately comes from that external source, not from the vacuum itself. This brings us to the central difficulty. While vacuum fluctuations are real and observable through indirect means, they do not represent a reservoir of freely accessible energy. The vacuum state is stable. Extracting energy from it would require transitioning to a state of lower energy. But if such a state existed, the current vacuum would decay spontaneously. The fact that it hasn't, over the 13.8 billion years of cosmic history, strongly suggests that our vacuum is already at or very near the lowest energy configuration permitted by the laws of physics. Theoretical proposals for vacuum manipulation sometimes involve exotic physics, such as hypothetical scalar fields, negative energy densities, or spacetime engineering. Wormholes, warp drives, and other speculative ideas rely on properties that extend or break from standard quantum field theory. These frameworks often require conditions that are not only technologically infeasible, but may also be forbidden by deeper consistency principles. Even if negative energy can be engineered in tiny, fleeting quantities, as suggested by some aspects of quantum inequalities, it cannot be sustained or scaled in a way that would permit perpetual motion or propulsion. Still, interest in vacuum manipulation persists, not just because of the dream of boundless energy, but because the vacuum is a foundational element of nature. Understanding it more deeply could lead to new technologies indirectly. Quantum optics, for example, leverages vacuum fluctuations to control photon emission rates, entangle particles, and develop sensitive measurement systems. Photonic crystal cavities and waveguides are being engineered to alter the density of states in the vacuum field, enhancing or suppressing interactions with matter. These advances don't extract energy from the vacuum, but they do make it a more active partner in how we manipulate information and light. Quantum metrology, too, benefits from the vacuum's properties. By understanding and accounting for quantum noise, an inevitable consequence of zero-point energy, researchers can design sensors and clocks of astonishing precision. Vacuum fluctuations set the ultimate limits of measurement, but knowing those limits allows engineers to approach them asymptotically. The result is quantum-enhanced technologies that exploit the vacuum not as an energy source, but as a constraint with structure, one that can be used as a ruler, a reference, or a control surface. There is also a growing interest in how the vacuum connects to information. In quantum information theory, the vacuum state is not trivial. It contains entanglement across regions of space, correlations that are non-local and deeply woven into the structure of quantum fields. Some interpretations of black hole thermodynamics suggest that the entropy of spacetime is encoded in vacuum entanglement. If this is true, the vacuum is not just energy-rich, but information-rich. Understanding that information could reveal how spacetime emerges from more fundamental processes, possibly guiding the development of quantum gravity. And so, even if the dream of harvesting the vacuum for power remains out of reach, the pursuit is not wasted. By studying the vacuum, we refine our understanding of energy, entropy, causality, and even the fabric of reality. We develop new tools for sensing, computing, and communicating. We clarify the limits of what can and cannot be done. The journey toward harnessing the vacuum may not yield engines or reactors, but it may yield insights that revolutionize our understanding of nature. It is also important to distinguish between energy availability and energy accessibility. The quantum vacuum may contain vast theoretical energy, but accessibility is constrained by the very laws that define it. These constraints are not arbitrary. They preserve unitarity, causality, and thermodynamic stability. Attempts to circumvent them often lead to inconsistencies, runaway solutions, or violations of fundamental conservation principles. In this sense, the vacuum is not a frontier to be exploited, but a structure to be understood. As we refine our theories, incorporating quantum field theory into curved spacetime and pushing toward a consistent theory of quantum gravity, we may uncover new principles governing vacuum behavior. Some proposals suggest that what we call the vacuum is not a unique state, but one of many, each with its own field content and cosmological constant. In this view, our vacuum is a local patch in a larger landscape, and transitions between vacua could have occurred in the early universe or could still occur in some distant region. While this multiverse picture remains speculative, it further reinforces the idea that the vacuum is not a simple void but a dynamic, structured entity. And if that structure can shift, even minutely, it may have implications for cosmology, particle physics, and the deep symmetries of nature. But even then, it does not imply extractable energy in the traditional sense. It implies evolution, possibility, change on a cosmic scale. For now, the vacuum remains a paradox. It is everywhere, and yet cannot be touched. It shapes everything and yet eludes control. It is both the quietest and most active place in the universe. And though we cannot plug into it as we might a battery or a fuel cell, it continues to illuminate our understanding of what is and what might be. Perhaps in a way, the vacuum teaches us a lesson not about power, but about humility. That not everything with potential must be used. That some structures are not meant to be broken, but to be listened to. And that the deepest truths may lie not in what we can take from the universe, but in how we learn to see it differently. Chapter 10. Is nothingness just an illusion? For centuries, the concept of nothingness has haunted both philosophy and physics. It is a word that implies absence, a complete void, a state in which not only matter and energy are gone, but so too is form, structure, direction, and even meaning. In the classical worldview, such a state was conceivable, a perfect vacuum, a container devoid of contents, perhaps the backdrop against which the events of the universe could unfold. But as science has evolved, so too has our understanding of emptiness. And in the realm of quantum physics, the idea of true nothingness begins to unravel entirely. At the most basic level, quantum field theory denies the possibility of a vacuum devoid of activity. Fields pervade all of space, and even in their lowest energy states, they do not sit still. They fluctuate, governed by the uncertainty principle, which forbids a precise specification of both a field's value and its rate of change simultaneously. These fluctuations give rise to transient excitations known as virtual particles, which flicker in and out of existence too quickly to be directly observed, but whose influence can be measured with extraordinary precision. This seemingly paradoxical activity in the absence of particles is not a metaphor. It is measurable. Effects like the Casimir force, the Lamb shift in atomic spectra, and the radiative corrections in particle masses are all physical consequences of vacuum fluctuations. If one were to remove all matter from a region of space, extract all thermal radiation, and isolate it from external influence, that region would still not be truly empty. It would remain filled with this jittery quantum foam, a ceaseless play of field activity with no permanent players. The vacuum in this view is not a static background, but a dynamical entity. It has energy. It responds to boundaries. It even helps define what counts as a particle depending on one's frame of reference. This realization radically transforms the philosophical implications of nothingness. If the vacuum teems with activity, if it has structure, if it can affect and be affected, then is it truly nothing at all? Or is it something too subtle, too foundational to be captured by that word? To understand this further, consider the nature of quantum entanglement. The vacuum state of a field is not merely a zero-energy baseline. It contains correlations, entanglements, between different regions of space. These correlations persist even when no particles are present. In fact, attempts to isolate a region of the vacuum from its surroundings reveal that such separations are always artificial. Quantum entanglement links seemingly independent areas into a unified whole. In other words, even what we consider empty space is knit together with invisible threads of connectivity. These are not mystical connections, but mathematically describable structures that arise naturally from the formalism of quantum fields. From another angle, general relativity teaches us that space itself is dynamic. The presence of energy and mass curves spacetime, changing its geometry. But quantum theory extends this idea by suggesting that even empty space possesses a kind of latent energy, zero-point energy, which influences the expansion of the universe. Dark energy, for example, is often interpreted as the energy of the vacuum itself. It does not vanish even when all particles are removed. It exerts pressure, causes cosmic acceleration, and dictates the large-scale fate of the universe. In such a setting, how could the vacuum be called nothing when it acts as the dominant force driving the evolution of the cosmos? Even more provocatively, some approaches to quantum gravity suggest that spacetime itself may be emergent from more fundamental structures. Perhaps quantum entanglement networks, causal graphs, or informational relations. In these views, the vacuum is not merely filled with something. It may be a manifestation of that deeper substrate. Space is not a passive emptiness, but a derived composite feature of more elemental entities. The apparent nothingness is actually a projection of deeply entangled, highly organized systems that underlie what we perceive as locality and geometry. This inversion, where structure begets space rather than the other way around, has become a serious topic in theoretical physics. The holographic principle, for example, suggests that all of the information within a volume of space may be encoded on its boundary surface. Originally derived from black hole thermodynamics, this principle has since found broader application in the AD-SCFT correspondence, a framework in which a gravitational theory in a higher dimensional spacetime is equivalent to a quantum field theory without gravity on a lower dimensional boundary. In this picture, spacetime and vacuum energy emerge from quantum entanglement patterns on the boundary. The emptiness inside is not primitive, it is derivative. It arises from information encoded elsewhere. Such ideas push the boundaries of physics, but they also speak to a deeper intuition. That emptiness is relative, not absolute. What one observer sees as vacuum, another might see as a bath of particles, depending on their motion or environment. The Unruh effect demonstrates this explicitly. The uniformly accelerating observer perceives the vacuum as a thermal state, full of particles at a temperature proportional to their acceleration. Meanwhile, an inertial observer sees that same vacuum as empty. Both perspectives are valid within their own frames. The vacuum is not a single object. It is an observer-dependent condition. This suggests that even the idea of nothing must be contextualized. It depends on who is looking and from where. This relativity extends into cosmology as well. During the inflationary epoch of the early universe, quantum fluctuations in the vacuum were stretched to macroscopic scales by the rapid expansion of space. These fluctuations seeded the initial density perturbations that later grew into galaxies and clusters. Thus, the very structure of the universe, its filaments, voids, and walls, can trace its origin to patterns of activity in what was once considered nothing. In a very real sense, the universe as we know it emerged from the vacuum. Not as a poetic metaphor, but as a consequence of quantum dynamics operating on an expanding geometric canvas. This transformation of nothingness into something, into matter, radiation, and complexity, underscores a profound shift in perspective. What we once thought of as absence has become presence. What we thought inert is active. What we thought cold and dead is teeming with hidden structure. Yet this also introduces a curious asymmetry. If the vacuum is full, where then is true nothingness? Can it exist? Is there any frame, any condition, any configuration that would correspond to a complete and utter absence? According to current theories, the answer seems to be no. Not only is there no known way to eliminate the quantum fields that define the vacuum, but there is also no known mechanism by which those fields can be turned off or removed. They are intrinsic to reality as we know it. In this light, nothing is not a physical state but a linguistic placeholder, a term we use to describe a lack of the familiar rather than a presence of the truly absent. It is an idea, not a physical condition, a limit in our conceptual toolkit, not in the fabric of the universe. Even mathematical formulations struggle with pure nothingness. Every definition, every operation, every boundary condition presumes a structure upon which it acts. There is no equation that describes nothing because equations require variables. There is no geometry of nothing because geometry presumes points, distances, relationships. The moment we attempt to formalize nothingness, it slips away, replaced by the structures required to define it. And so we arrive at a paradox. The universe appears to be filled with something in every corner, even if that something is only the dynamic whisper of a quantum field or the entangled web of vacuum correlations. We can never truly step outside of existence to glimpse its opposite, because any act of observation, any framework of theory, is already a participation in being. This realization may disappoint those who seek a clean duality between something and nothing, but it also opens the door to wonder. If even the vacuum is alive with structure, then perhaps there is no edge to meaning, no final subtraction that leaves us with true void. Instead, there is only the unfolding of forms, the layering of states, the transformation of potential into presence. Perhaps, in the deepest reaches of space, where matter thins to nearly nothing and light barely travels, we find not emptiness, but continuity. A continuum of activity too subtle to detect, too vast to measure, but always there. Moving, connecting, becoming. And perhaps this tells us something not only about the universe, but about ourselves. That what we take to be silence may be a form of music we haven't yet learned to hear. That what we call nothing is merely the background hum of everything. If you're still with me, friend, then maybe sleep hasn't found you yet. If you're curious to keep drifting, there's another video waiting, just a quiet journey away. But if your eyes are already heavy, then may your dreams be soft, and may you float gently among the stars. Good night, and sweet dreams among the stars.